All right, welcome to the Packets 101 portion of our Intro to Networking course. Let's begin. So let's talk about what a packet is. A packet at its core is simply a unit of network data transmission that is read by another device from the first bit to the last, remember our ones and zeros, as it is transmitted. So one device will transmit the packet across some sort of media, a fiber optic cable or a copper cable, and there are others, radio waves. And the device at the other end should receive that information. Like we talked about earlier in the previous video, packets are fundamentally comprised of ones and zeros. That's the core unit of transmission, and that gets encoded onto fiber optic cable as light impulses, or electrical as electric voltage changes. And different part of the packet can be described by different protocols or standards. So what we're going to see going forth is that there will be a standard for the layer 2 portion of the packet, layer 3 portion of the packet, layer 4, layer 7, and different standards can be used. Different protocols can be used in those spaces. Okay. The packet's headers go first because they provide data about the payload of the packet or the layer 7 contents. And all these layers will make more sense in just a second. We're going to get into detail on what those layers are, but our big layer 7 there over on the right, that's what we actually want to transmit. That's the message. The front part, the part we're kind of representing over here on the left, describes, address information or things we need to know before we actually to get this message to its destination. Okay. Let's talk about the OSI model. This is kind of a weird concept when you're first learning at networking. You're like, why is it? And the funny thing about the OSI model is it's never actually used in real life. You'll never see a computer that has software for the OSI model or anything. But the OSI model is a theoretical model that we use to describe the function of different network gear and network protocols. At the bottom of the model is the physical layer. So standards and components that refer to the physical transmission of the packet over a copper cable or fiber optics and things like that. Layer 2 is the data link layer. And this is mostly used, like Ethernet is a data link protocol layer 2. Switches operate at layer 2, most classically. Layer 3 is the network layer, and that's for IP devices and routers. The routers are typically layer 3 devices. Routing is a layer 3 function. Above that is the transport layer, and we'll talk about this a good bit later in the class, but not in this video. That's TCP, UDP nowadays, or layer 4 firewalls. Then come the presentation and the session layer, and people try to plug different protocols into here, but the truth of the matter is these two layers aren't used as much. We could maybe put something in there like SSL encryption for HTTP, but anyhow, we won't go much more into that. And then layer 7 is the application layer. So that would be any of your application protocols like HTTP for the web, or HTTPS, or SSH, or Telnet, or SNMP, or syslog, or anything that actually is the contents of the packet is used by the application. That's kind of considered the message there. Okay. So going from the OSI model, we have what we call the TCP/IP model. And this is a more real-world model. This is kind of what things look like more in the real world here. So they're missing our layers 5 and 6. Layers 1 and 2 here are kind of combined into what they call either the network access or the network interface layer. And you'll see the same types of devices. and types of protocols kind of correlate here. Network layer, or the internet layer, it's sometimes called in the TCP/IP model. Transport is the same, and then the application layer takes up 5, 6, and 7. This is more like what we'd see in a typical packet. This better describes a typical network frame that you'd see. So a quick note, the reason that we talk about Ethernet and the IP, Internet Protocol, and TCP, UDP, is that this set of standards, this kind of protocol suite, if you call them, group of protocols, has become dominant all over the internet and in most modern networks. What kind of happened over the years is there was a lot of different competing standards, and TCP/IP and Ethernet really won. That doesn't mean that others are not used. They still are in cases, but those are the big ones. Okay. And one of the things kind of that we talked about before, but having a theoretical model like the OSI model just gives us a good framework to plug in different protocols in the stack. So we can have some terminology in the network industry to compare different protocols and say, well, is this a layer 3 thing? Is this a layer 2 thing? So you hear that constantly in the industry. Let's talk real quickly about layer 1 before we move up the stack. Layer 1, like we said, is the physical layer. It talks about the physical media that's used to transmit data. So this could be for long distance work. We have fiber optics often, or in data centers. Anytime you need to go a long distance, and this is light sent over little strands of glass. The other nice thing about fiber optics is they tend to support the fastest speed. So when we talk about 40 gigabit and 100 gigabit, you're getting into the space that today is really occupied by fiber optics. Copper, just twisted pairs of copper cables is what we use today. These use electricity at real low voltages, send over thin copper cables. They can't go quite as far. You see a lot of these connecting to computers, obviously, an access point. And then wireless. Now we have protocols that use radio waves to transmit data, which is great. And there's others out there. There's lasers that can be used to transmit data. There's coaxial cable. You could use carrier pigeons if you really wanted to. It's all physical media. Let's talk about packet terminology. Let's define some terms here. So layer 1 is the physical layer. So we won't represent that. That just is assumed as the underlying physical carrier that we use to send this data, if that makes sense. So often we use packet and frame interchangeably, but technically speaking, the layer 2, 3, 4, and 7 portion, this whole thing right here, is called a frame, if we include all of it. If we take the layer 2 header off, and we just have layer 3 through 7, it's a packet. If we take the layer 3 header off and just have layers 4 and 7, that's called a segment. A lot of times you're going to hear packet used as the primary descriptor. People use packet when they really mean frame, but that's okay. We'll use them semi-interchangeably here unless we have to really be specific about what it is. But frame includes layer 2, packet just layer 3, and so on and so forth. So let's talk about addressing. In our previous video, we talked about addresses, but we just used, A and B and C. In this video, we'll really dive in here and talk about what those addresses really are in modern networks. We said Ethernet is the dominant layer 2 address, and IP addresses that's really won the role of the layer 3 address. But the question is, why do we need two types of addresses? This is how a real packet will look. You'll see a layer 2 portion and a layer 3 portion. Now there's more in these portions than just the destination and the source and the destination. That's how they're written, by the way. In the layer 2, the destination comes first. There's more in the packet that we're not seeing, but we're kind of simplifying it right now. But why do we need two sets of addresses? That's kind of weird. Well, let me introduce the concept of local versus global addresses. And this is really important. we use two types of addresses so we can construct a packet that tells us where to go next, local delivery, and also where our ultimate destination is. So we talk about what our next hop is, router to router to router to the end device in this illustration. But all through that, see this red line here, we want to maintain our idea of a final destination. Okay? So if there's a bunch of different routers here in the internet, like there is in the internet, our next hop, our layer 2 address, would just tell us where to go next. And then this device would replace that header. Well, we're getting a little bit ahead, but replace the layer 2 addresses and say, go here now, and go here now. Those are hops along the way, but the whole time the layer 3 address would remain consistent. Okay? So, again, let me restate it. The layer 2 header, part of the packet, and the layer 2 addresses are concerned with local delivery, hop to hop to hop. Layer 3 header is concerned with global delivery, source to destination, say across the internet or across your organization or your home or whatever. So let's look at our Ethernet frame again here. Remember, we're reading the packet from the beginning to the end, and what's inside these packets are ones and zeros. Now, let's talk about these headers a little bit. Layer 2, the switch only looks at the layer 2 header when it's making its decisions. Switch only looks at layer 2. It ignores the rest of the packet. It just transmits it. A router will look at the layer 2 header and make sure the packet is actually destined for itself before it does anything. And then it will remove the layer 2 header. It then looks at the layer 3 header for global delivery and figures out where to send the packet next based on its routing table. We'll talk more about that. And then it leaves the layer 3 header unmodified. So the layer 3 header stays. It just has been inspected, but it stays on there. And it puts a new layer 2 header with a new source and destination back on the packet. So routers take the layer 2 header off, look at the layer 3 header, put a new layer 2 header back on. Some routers, and this is a little bit advanced, but can actually look at the layer 4 header and make some decisions. They typically won't do anything to the layer 4, just like we talked about with layer 3. They'll leave it well enough alone, but they can look at it and make some decisions. Firewalls, really advanced routers that filter packets, will almost always look at the layer 4 header. And some advanced firewalls can actually look at the entire packet all the way into layer 7 to make their forwarding decisions, whether or not they want to forward or maybe just throw away a packet because they're blocking certain types of network traffic. Okay, let's talk about what the layer 2 address really is. Well, it's the MAC address. The Ethernet standard, IEEE 802.3, specifies this media access control address to be used as the source of destination address for each layer 2 frame. Okay, the MAC address is a 48-bit number, and we'll see that upcoming here. That's 6 bytes, so 48 divided by 8 is 6. And we'll typically write the MAC address in the following format, as we show down here: 00:11:22:AA:BB:CC. So, remember, computers like ones and zeros, but we as humans don't. Look down here. I mean, this string of ones and zeros, if I had to tell you my address, that'd be really hard. It would take forever, and it's 48 ones and zeros long. So what we do is we convert from a base 2 numbering system into a base 16 numbering system. We call it hexadecimal. In hexadecimal, 0 through 9 and A through F are all valid characters. All right. Here's some just some formatting stuff here. Here's the MAC address with colon delimiters. Here's the MAC address without any delimiters. Sometimes you see this different ways. Sometimes you see a period every 4 characters there. And then again, here's the MAC address with just a strings of 1 and 0. So this is what the computer or the router or the switch sees. Without any of the spaces, just a string of 1s and 0s encoded over light for fiber optics or electrical signals. A little more about formatting. We're in our hexadecimal format here. The first half of the MAC address, what we call the organizationally unique identifier, is assigned by the manufacturer, or assigned, to the manufacturer of network equipment by an organization called IANA, the Internet Assigned Number Authority. So they give out this first part to anybody who wants to build network equipment. The second half of that MAC address right up here is given out by that vendor of equipment and put on each network interface. And they do this uniquely. So each device across the entire world should, again, there's always a few exceptions here, but should have a unique address for local addressing. It should be globally unique. But we're using that term kind of confusingly because layer 3 addresses are global addresses. But MAC addresses should be handed out uniquely to each network device. If your computer has 2 network cards, maybe a wired port for Ethernet and a wireless port for Wi-Fi, it'll have 2 MAC addresses, anything that talks on a network. Let's talk about the layer 3 address, the IP address. It stands for Internet Protocol. Specifies a 32-bit or 4-byte, 32 divided by 8 is 4, address. And it's written in decimal, base 10 numbering system. So you won't see any of the A through Fs here. So the lowest number you could have in an IP address is 0. In each one of these 4 slots, the highest is 255. So 255.255.255.255. Now, we're going to talk in the next few slides. There are a bunch of these numbers that are reserved. So you really don't get a la carte use of the IP space. There's some reserved addresses. Each IP address should be globally unique across the entire internet. Of course, everything has exceptions. Just as with the MAC address, we can convert to binary. Remember, the decimal numbering system, the 0 through 9 is just for us humans because we like decimal. We like 10-base numbering systems. That's how we were taught, and that's kind of how our brains are programmed. We have 10 fingers. But here is this address above in binary. So this means 8 and 8 and 4 and 4. Some ranges of addresses are reserved. They are reserved in a request for comment. This is just a special type of a document that's published through a group called the IETF, the Internet Engineering Task Force. 1918, a fairly famous RFC document. They're all numbered. So the 10 dot addresses are reserved. The 172.16 through 31 is reserved, and that'll make more sense when we talk about these little guys, the subnets here. And then 192.168 is reserved. Those are reserved for private use within an organization. They can't be allowed out onto the internet. Now there's some more reserved addresses. These are all reserved. We have IP multicast space. The ones in red are some of the more common ones that you know are reserved. But yeah, these are all reserved, different RFCs that set them aside. Loopback addresses, link local addresses, 0 configuration. Different things are here. The red ones are the most common. The white ones are not as common. You don't run across those use cases typically as often, but they are reserved. So let's talk about building out a frame here. So to construct a packet, the device needs four things, and we kind of alluded to this in a previous slide. It needs its own MAC and IP address, which it should already know. So my IP source and my MAC source. So there's my MAC, there's my IP. The X's mean we already have this information. It also needs the destination IP address of the server out there on the web that it wants to talk to. What it often does is use a protocol that we'll talk about in another video called DNS, and it goes out and says, hey, server out there, what if I wanted to go to www.google.com, what IP address should I go to? And DNS has the job of returning that IP address. So often we find the IP address of our destination through DNS. Not always, but often. That leaves us with the MAC address. We have to find the destination MAC address that we're going to. And that's often provided by the address resolution protocol, right? Appropriately named, it resolves addresses, and it's a protocol. Here's all that the address resolution protocol does. It sends out a broadcast. We talk about broadcast packets in our previous video, and says, hey, could the device with this IP address tell me your MAC address? And it sends it out as a broadcast. So it sends it out to everybody within its broadcast domain, everybody within earshot, everybody on its network segment. Anybody with this IP address, tell me your MAC address. And then if there's such a device out there, the answer will come back and say, hi, I am this device and I have this MAC address. Okay. So now that we have all four pieces of required information, our frame is complete. We can complete a frame. We can put in the source IP, the source MAC address, and the destination IP and the destination MAC address. We have all that information, and the computer assembles that, or whatever device you're using. All right, well, that's all for this portion of the video. In the next video, though, we're going to talk more about IP specifically, and subnets, and broadcast domains, and how the layer 3 address works in quite a bit of detail. All right, thank you.